All right, so in this lecture, we will do the examples of Hodge duality, and we will do the two important cases, the n equals 3, and the inner product on V is signature, 3, 0, and we will do n equals 4, where the inner product on V has signature 3, 1, right? So actually, sometimes these signatures, by the way, are written with three numbers, 3, 0, 0, and 3, 1, 0, where the last one is the number of zero eigenvalues, the middle one is the number of negative eigenvalues, and the third is the number of positive eigenvalues. But rarely, I don't know if I recall any circumstances where the zero eigenvalues come up. It is possible, of course, and so, but we'll just, the signature is this, and so S is the number of positive eigenvalues, so that's the first of these numbers. And we'll use 3, 1 instead of 1, 3. It turns out it won't matter much because it's really the evenness or oddness of S that plays a factor in all this. So we'll do those examples. Let's start with the example of n equals 3. So with n equals 3 in the coordinate basis, we'll have a top form, and we'll say that that gives us our volume dx1 wedge, dx2 wedge, dx3. That'll be our volume form, and that'll be our positive volume form. And so now we're just going to ask ourselves, well, what's the Hodge dual of all of the relevant forms? So let's look at the one forms, right? And we could just go right to our formula, by the way. So I could say the Hodge dual, well, I should probably write down what the one formula is. The Hodge dual of dx, I'll write down the formula, dxi1, all these wedges, to dxip is equal to epsilon I h, and then it's these ei1 in V star EIP in V star, and then it's dxj1 wedge wedge dxj n minus p. Phew. So that's the formula, right? So let's just apply it, right? We're going to now look for the one forms. So on this side, putting a one form here, oh, I'm sorry, and it is the Hodge dual. And if I want to be fancy, I say it's the P-Hodge dual. So we're going to do for one form. So I'm looking for the Hodge dual, or I'll suppress this little p now, of dx, say, oops, not p, dx, well, let's do dx1, right? Okay, so the epsilon symbol, well, I, multi-index I, is just 1, right? That's all there is. So what's in H? Well, H is everything left over. So there's 2 and 3 left over. So I'll just pick an ordering. I'll pick 2, 3. Doesn't really matter what ordering I pick of these J's. This epsilon will take care of the sign that's induced by flipping the J's out here. So I have 2 and 3 left over, so that takes care of that. What's interesting here is I'm dealing with a Riemannian interproduct, right? Riemannian, it means every one of these terms is always going to be 1, right? So for this universe where we have dimension 3 and a positive, well, this inner product of signature 3, this stuff here is always going to equal 1 because it's a product of terms that can only be 1. So I'm just going to ignore it for now. I won't, since I want to bring it back later, I'm not going to cross it out. But we ignore that. So just to show that it's there, but it's always equal to 1, I'm going to throw it in this blue, just to remind you that that product is there, but always equals 1. And then what's the last part? Well, the last part is I chose an ordering of 2, 3, so I have to go dx2 wedge dx3. So what's the value of this guy? Well, the comma there is just to tell us to concatenate these things, so that's equal to E1, 2, 3, which equals 1. So the Hodge dual of dx1 is going to be dx2 wedge dx3. Simple as that. So what about the Hodge dual of dx2? Well, this can almost go, I put the 2 there, right? Because that's the multi-index I. The multi-index I is 2, right? Because that's what's on the left-hand side. These guys here form the multi-index I. That's the definition of what I is. Since that was last lecture, I should write down that, I is the multi-index represented by I1 through IP, and H is the multi-index of the complements J1 through Jn minus P, where there's no overlaps, right? It's the complement, it's the guys missing from this list appear in this list. So now, 2, so let's go with 1, 3. I always like these strictly increasing versions of things. That factor of 1 still comes down, which I'll just go ahead and put there. And then this will be dx1 wedge dx3. So what's the value here? What is epsilon 2, 1, 3? Let's see, 1, 2, 3. I'm going to count the number of flips between 1, 2, 3 and 2, 1, 3. Whoops, it's 1 flip, which means this guy equals negative 1. So it's minus dx1 wedge dx3. That is the Hodge dual of dx2. Like that. Now, in engineering notation, I keep saying engineering notation, but what I mean is stuff that I saw in the most elementary textbooks, or introductory notations, or those treatments that only treat n minus 3. In those cases, they usually don't go with x1, x2, and x3. They go with x, y, and z, right? So this whole thing would be written dy equals dx wedge dz. But you don't need to have this minus sign there. You can just write it as dz wedge dx, and you've got the same thing. You've just flipped the sign by flipping the order, and it gets rid of minus signs. So very frequently you'll see it written that way, right? You'll see all of the Hodge duals expressed in a way where there is no minus sign in front. However, since we are using this sort of space-time index notation, and I have this preference for this strict basis, I kind of want to keep this basis vector as a strict basis vector. So I'm going to keep the minus signs and keep the strict ordering when it's feasible to do so. So so for now, that's just my preference. Okay, so I guess the last one then would be, why not, dx3, and that's going to be epsilon 3, and then the strict ordering would be 2, the strict ordering is 1, 2, and I'll drop down the 1, dx1 wedge dx2, and 3, 1, 2, let's see, 1, 2, 3, 2, 1, 3 is 1 flip. What do I want? I want 3, 1, 2. Okay, so I go 1, 3, 2 is 1 flip, 3, 1, 2 is another flip. So there's 2 flips, so it's positive, so it's dx1 wedge dx2, like that. So that's your Hodge duals of your basis 1 form. So now any 1 form, which is a mu dx mu, like that, any 1 form, the Hodge dual of that thing is going to be, well, let's see, it's a1 dx1 plus a2 dx2 plus a3 dx3, which is going to be a1. So now the Hodge dual of this, I guess I'll write the Hodge dual 1. The Hodge dual of this is going to be a1 times the Hodge dual of dx1 plus A2 times the Hodge dual of dx2. This is the linearity in action. A3 times the Hodge dual of dx3, like that, which is going to be A1 times dx2 wedge dx3 plus A2 times minus dx1 wedge dx3 plus A3 dx1 wedge dx2. So the Hodge dual of a 1 form ends up being a 2 form, and it's exactly this 2 form. I could take that minus sign and change this to a minus sign if I want to. Well, I do want to, so I should, but regardless, that's how you do it, right? Once you know the Hodge dual of the basis vectors, you can find the Hodge dual of an arbitrary 1 form. So that's the 1 forms. The 2 forms, same process, right? If I want to know the Hodge dual of the basis dx1 wedge dx2, I'm going to now do 1, 2, and then there's only one thing left in J, in the list J, and that's 3. Again, nothing changes about this thing, right? Although the list now has there's 2 inner product terms in this, there's 2 factors in this multiplication of inner products. Down here, this one, there was only 1 factor, right? This would have been E superscript 2, E superscript 2, the inner product. This would have been this one would have been E superscript 1, E superscript 1. But there's only 1 factor because the length of the list, P, was only one long. Here, the length would be 2 long, but it doesn't matter. It's still 2 factors of 1. So I'll still keep that thing in there. And then there's only 1 term left over, and that's dx3. But epsilon 1, 2, 3 is just 1, so this equals dx3. So that was that one. Then I guess there's dx1 wedge dx3, right? The Hodge dual of that. And that's going to be epsilon 1, 3, 2, 1, and then dx2. And that's going to be 1, 3, 2. That's 1, 2, 3. Getting to 1, 3, 2 is obviously 1 flip. So it's minus dx2, right? And then, let's see, the Hodge dual of dx2 wedge dx3, which is the last one, is epsilon 2, 3, 1 times this factor of 1, dx 1, which 1, 2, 3 to 2, 3, 1. Let's see, how does that work? We do 1 flip to 2, 1, 3, and then another flip to 2, 3, 1, which is 2 flips. 2 flips. Notice I don't have to go through every possible way of getting there. If it takes 2 flips in any way, or an even number of flips, it doesn't matter how you do it. It's always going to be an even number. That's the whole point. That's why it's robust, right? It's unique, right? Every permutation is unique. No matter how you roll from the original permutation to the final permutation, you're forced into an even or odd number of flips, depending on the nature of the change. And so, okay, so that's even, so this is just going to be dx1. Okay, so those are those Hodge duals. And again, I can take any alpha, or A alpha beta, dx alpha wedge dx beta, and I write this down as alpha 1, 1, well, not alpha 1, 1, because that would be dx1 wedge dx1, which is 0, right? So that's not going anywhere. Alpha 1, 2 dx1 wedge dx2 plus alpha 1, 3 dx1 wedge dx3 plus alpha 2, 3 dx2 wedge dx3. And now if I, now if I want the Hodge dual of that thing, again, linearity saves the day, makes it easy at this point. it's the Hodge dual of this guy, dx1 dx2, which is dx3, plus alpha 1 3 times the Hodge dual of this guy, which is minus dx2, and then it's plus alpha 2 3 plus the Hodge dual of that guy, which is dx1, right? So 1 3, and that's all, right? That's what it is. And of course, this is a 2 form, right? So it's going to 2 form going to an n minus 2 form, which is a 3 minus 2 form, which is a 1 form, and that's what that is, a 1 form. And of course, in each circumstance, the 1 form is balanced, where, remember, the Hodge dual contains all of the terms all of the coordinates that are not in the original vector, right? So in this case, it's 1 and 2. Well, the one that's missing is 3, and of course, that's what you get. 1 and 3, the one that's missing is 2. The question is, what's the sign, right? And that's what we figured out initially. We figured out the sign. That's what gets it all right. So that's how you take the Hodge dual of an arbitrary 2 form. Now, what's really important to see here, that's really interesting, is that lambda 0 is 1-dimensional, lambda 1 is 3-dimensional, but lambda 2 is 3-dimensional also, and lambda 3 is 1-dimensional. The fact that these two have the same dimensionality, and the Hodge dual of 1 and 2 are the same, that's well, the dimensionality of p and n minus p is always the same. This makes perfect sense. Okay, and then ultimately the Hodge dual of this guy, you can still run it through the same equation, although we know the answer from a previous formula, but let's just do it. dx1 wedge dx2 wedge dx3. Consider the Hodge dual of that, and I'll do 3. It's going to be epsilon 1, 2, 3, comma, there's nothing. There's nothing to put on the other side of that. It's a 0 form, right? So there's no indices on a 0 form. So you just leave it to 1, 2, 3. I'll put the comma there to show that I at least thought about it. The 1 still comes down. And what's the basis of the 0 forms? It's just the number 1. So so the Hodge dual of dx1, 2, 3 is simply 1, right? And that agrees with our expression that we had before, minus 1 to the n minus s, where in this case it's 3 minus 3, which equals minus 1 to the 0, right? And so sure enough, that works. So the Hodge dual of any alpha, I'll just put a dx1 wedge dx2 wedge dx3, that's any member of the top form, exterior third power, is going to simply equal a times the Hodge dual of this, which is a times 1, which is the number a. So you just peel off this number a and you get the Hodge dual of the full 3 form. Okay, so that's the n equals 3, s equals 3 case. So now we'll do the next case. So now we're going to do n equals 4, s equals 3. So we're dealing with a 3-1 pseudo-Riemannian metric. And so we'll start again. I better write down, let's see, I'll go back here. Oops, not here, but here. And let's see, this, hold on. This formula here, this formula here is still our operating formula, right? So I'll put that up there. And we're going to do the same thing. We're looking for dx, well, let's see, I'm using n equals 4, so I'm going to go with dx0, because in Lorentzian, when we do this Lorentzian thing, we tend to start with 0. So I'm going to go with dx0, and I'm interested in the Hodge dual of that thing. And this time I'm going to get rid of this. You know, the Hodge dual, clearly this Hodge dual operator is the one that's operating in the first exterior power space, right? So the Hodge dual of that is going to be the same thing, epsilon 0, and then I'll just take arbitrarily, I'll take the strictly increasing remaining things. But now I do have to kind of worry about these inner products because they're not all 1. Some of them are -1. But in this case, the one that this sequence, or this, not sequence, this product of inner products is, the number of them is p. Well, we're dealing with the pth exterior power on this side, which means we only have 1. This string is 1 long, but it is E0, E0, V star, right? So that's important because in our pseudo-Riemannian metric, we always take, well, I shouldn't say always, but we're going to take E0, E0, V star. That's the one that equals -1. The rest of them, EI, EJ equals delta IJ, where I and J are 1, 2, and 3, right, from that set 1, 2, 3. So this is the one that actually equals -1. And then I have dx1 wedge, dx2 wedge, dx3. Now notice that this is how it's supposed to work, right? This is a 1 form. The Hodge dual of a 1 form in 4 dimensions is an n minus p form, where p is 1, n is 4, so 4 minus 1 is 3. So this thing here has got to be a 3 form. Well, there it is. There's your 3 form. It's built of it's a string of the 1 forms that are not part of this string, so of this sequence. The sequence being the single index 0. So you have 1, 2, and 3. The ordering I chose arbitrarily. As long as this ordering is the same as this ordering, I won't make a mistake doing that. This guy turns out to be 1, right? Because the sequence 0, 1, 2, 3, no flips, 0 is an even number. So that's good. This guy turns out to be -1, though. -1. And then you have dx1 wedge, dx2 wedge, dx3. And so this is negative dx1 wedge, dx2 wedge, dx3. So the Hodge dual of dx0 equals the opposite of dx1, dx2, dx3. And like I said, if we were doing this in, maybe if we were just studying pure special relativity and we didn't want to carry around all of these superscripts, we might write this way. dt equals dx wedge, dy wedge, dz, oops, minus sign. And then we might say, let's do dx wedge, dz wedge, dy, something like that, just to get rid of the minus sign. I'd rather keep the ordering myself. Okay, so that's one of them, and then of course, now let's just do one of the remaining ones. Let's do, say, dx2, and dx2 is going to be epsilon 2, and then I'll take 0, 1, 3, since I always like to use the increasing system, but again, it's arbitrary. The product that I'm interested in is E2, E2 on V star. And then this would be dx0 wedge, dx1 wedge, dx3. And so now I have 2, 0, 1, 3, 1, 0, 1, 2, 3. So I have to get from here to here. Is this even or odd? Well, the 2 basically is going to the front. So it's 1 flip, 2 flips, right? And then you end up with 2, 0, 1, 3. Yeah, so it's 2 flips. 2 flips is even. So this is even. This is 1, so I have 1 times 1, dx0 wedge, dx1 wedge, dx3. Okay, so that's the Hodge dual of dx2. And I won't bother showing you how linearity allows you to convert any one form a mu dx mu into its Hodge dual, because it's just linear in exactly the same way that that these guys were linear here. All of this stuff here that we showed, the linearity, the same thing applies. The same thing applies in 4 dimensions. So linearity is sort of a trivial concept at this point. Okay, so that's the deal for 1 forms in 4 dimensions. For 2 forms in 4 dimensions, Hodge dual dx0 wedge dx1, epsilon 0, 1, and then what's left? 2, 3. 2, 3. The product is going to be E0, E0, V star, E1, E1 in V star in the dual space. And then what's left? dx2 wedge dx3. You do understand the ordering of the coordinates here, all it has to do is match the ordering there, and then this guy takes care of the sign. And so E0, 1, 2, 3, well, that's easy. That's obviously equal to 1. So that equals 1. This equals minus 1, and this equals 1. So this whole thing equals minus dx2 wedge dx3. And now you see the self-duality, right? Well, not that it's hard to see, it's obvious, right? This is p equals 2, and this is n minus p, which equals 4 minus 2, which equals 2. So this is the fact that the second exterior power, in the case of n equals 4, regardless of the nature of the metric, it's self-dual. It goes back into itself. But this is still dual in the sense of our pure definition from the beginning about matching up inner products with the wedge product into the top form space. That whole definition we did last time. And here you see it. 2 form, Hodge dual ends up being a 2 form. So that was this part that we had the little arrow going back to itself in the last lecture. Okay, and then I'll just try one to show you how the signs kind of work out. I think it should be that if I do dx0 wedge dx2, I think that should work out to have a positive sign here, where 2 negatives cancel out in a kind of interesting way. So I get epsilon 0, 2, and then what's left? 1, 3, and then I get E0, E0, and V star, and E2, E2, and V star, dx1 wedge dx3, like that. And then this guy, 0, 1, 2, 3, going to 0, 2, 1, 3. What is that? That's 1 flip. That's 1 flip. Just I flip these two and I get it, right? So 1 flip is odd. So this is minus 1. This guy here, that's minus 1. And this guy here is 1, right? So then dx1 wedge dx3. So that's dx1 wedge dx3. So here's a case where the Levi-Civita stuff that tracks these indices contradicts the sign flip driven by the pseudo-Riemannian nature of the metric, right? And you end up with a positive sign. So you end up with the Hodge dual. I guess you have to keep the braces there. dx0 wedge dx2. The reason you have to keep the braces there is if I did this, dx0 wedge dx2, you might think that it's still legit to say that the Hodge dual of this can be wedged with that, right? I mean, because the wedge product doesn't care if these are in different vector spaces. In fact, that's the whole point of it being sort of the algebra, the exterior algebra allows you to do that. If you remember that lecture on exterior algebra, the wedge product actually goes between these vector spaces. So unless you put the braces there, you don't know. You're taking the wedge product and then the Hodge dual, right? And again, it's self-dual, so you're seeing the result being in the same vector space as the argument of the argument of the left-hand side is in the same vector space as the right-hand side, which is sort of the range of that operator. All right, so that's for the second exterior power. For the third exterior power, now you can actually, with n equals 4, you can find something interesting for three forms, right? For three forms, because you haven't reached the top form yet. So I can take the dual of, say, dx0 wedge dx1 wedge dx2, and I can take that dual, and I would get epsilon 0, 1, 2, comma 3, right? Now the list J only has one element in it, but the list H only has one element in it. Remember, because this was E, I think I, H in our first lecture, or our previous lecture. So this thing, yeah, so there you go. And now you have three different guys in here. E0, E0, E1, E1, E2, E2, right? And you have dx3, right? So this ends up being, this Levi-Civita symbol is obviously 1, 0, 1, 2, 3, has 0 flips to get back to 0, 1, 2, 3. This guy here is driven to be -1 by the presence of this dude in the front. These two here are 1. And you end up with dx3, and you got minus dx3. And, just always good to check. You're dealing with, what are you dealing with? You're dealing with a 3 form. The Hodge dual for 3 form is a 4 minus 3 form, which is a 1 form. That's what's on this side. That's just a constant, of course. You always check that just to make sure you are tracking with what's going on here. And then I guess I'll just do one where it turns out to be positive. Again, the same thing kind of happens. dx0 wedge dx, let's say 1, 3, I guess is what'll, if you do it dx1, 3, basically end up with 0, 1, 3, 2, right? 0, 1, 2, 3 to 0, 1, 3, 2 is one flip, right? So that's going to end up being -1. This product in here will be -1, right? As long as you have this first term in there, it's going to be -1. So as long as a dx0 shows up on the left-hand side, this product here is always going to have a -1 in it. So this will be -1 times -1 dx2, so that's going to be just dx2. All right, so that's how it's done for 3 forms. So that's the 2 cases for your, all physicists should know these 2 cases. They're also just good exemplars of the rules. I guess actually what is sort of interesting is you can have a look at this double dual of 1 in this circumstance. That's kind of worth doing because, well, let's do it this way. What's the dual of 1? Well, that's going to be epsilon. Well, 1 has nothing, so it's 0, and then it's 0, 1, 2, 3. And there will be, in this, there'll be nothing, this will be a 1, nothing here. And then this will be dx0 wedge, dx1 wedge, dx2 wedge, dx3. Actually, wait a minute. This formula that we use, this formula that we've been using, basically here, probably not a good idea to apply it to 1. Remember, it was kind of designed for p being greater than 0. So let me, I'm going a little too quickly here. That's not the right thing. We know, I've already shown to you that the Hodge dual of 1 is always going to be the positive volume element. So we know that that's dx0, dx1, dx2, dx3, right? Now you could definitely throw in an epsilon in there, right? You could throw an epsilon ij, well, let's not go into it. But this is always true, right? So now the question is, what's the Hodge dual? Why is this always true? Go back to the last lecture, and we showed that this was true for every circumstance, regardless of the nature of the metric and regardless of the dimensionality of the space. This was always true. The point was this, what's this guy, right? So this is just the Hodge dual of dx0 wedge, dx1 wedge, dx2 wedge, dx3. Now, which is, see, this equals, I'm sorry, got to get this right, equals this. And this guy we showed was equal to minus 1 to the n minus s of 1, right? So that equaled, in this case it's 4 minus 3, which is 1, so it's minus 1. Right? So here's that case where you're dealing with the double dual of something does not necessarily equal something. It equals minus something. And that all depends on the signature again, right? And this formula, by the way, came from the last lecture, right? The equality between this Hodge dual here and this came from our last lecture. All right, so we've covered those two cases. What do you think, what is next? So you can't really discuss the notion of Hodge duals in the elementary case, the n equals 3 with the Riemannian metric with signature 3, 0, without talking about the cross product, right? I mean, if you don't know the connection between what we're doing now and the cross product, it's almost like, you know, you've got a pretty big gap there. I mean, the idea is this connection is actually kind of important because everybody learned ultimately in elementary physics. If I have a vector v, I can take the cross product, I'll do it this way, vector v, the cross product with a vector, say u, right, and I'll get another vector w, say. And this is now the cross product, not the Cartesian product, but the cross product, right? This is overloaded, right? This could, you know, this is a weird form of overloaded operator, though, because you could talk about the Cartesian product of a vector and another vector. That would just simply be the ordered pair uv, right? So this is a case where the arguments do not distinguish between the two operations, because you could also talk about the vector cross product, which is different. So this is not an overloaded operator. This is truly an ambiguous operator in this case, this little x. Although I think the Cartesian product is in typeface is usually a nice big X, where the cross product is sort of a little x. Anyway, the point is it's ambiguous in my scribbly writing. So I'm going to now assert this cross product we always remembered with the rule, let's see, I'm trying to remember the rule I learned. I cross j equals k, where these are all the unit vectors, I, j, and k, in a right-handed system. So I cross j equals k, j cross k equals I, and what is it? It's k cross I equals j. Is that right? K cross I equals j, yeah. So this was the cross products. So it's basically a vector operate on vector to get vector, right? So this actually arises from the algebra we've just done, because what we're really talking about, now we'll consider our vectors, our unit vectors, I guess what we were calling E1, E2, and E3, or dx1, dx2, and dx3. These are the bases we were using. We can use ijk like the engineers do, right? That's not a problem. We'll just call them ijk. We're not talking arbitrary dimensions. We're fixing ourselves into 3 dimensions. 3 symbols is a lot easier to write than this stuff. So let's just go with ijk. So if we did that, we could talk about I wedge j. And now we're talking about 2 vectors, right? So in this case, we'd be talking about an element of the first exterior power of the vector space V with the subscript down. But all of this works both ways, up and down. So we can talk about that wedge product. But the problem is that is an element of 2, right, of the second exterior power of the vector. So the wedge product took us from there to there. Well, how do we get back to there? Well, we take the Hodge dual of it, right? The Hodge dual of it. And once we do that, now we're back into the original space. So what's the Hodge dual of ij? Well, okay, I wedge j, Hodge dual is going to be epsilon I j k. Again, we're dealing with pseudo-Riemannian, or Riemannian, regular Euclidean. I should say Euclidean, not, although they're kind of the same. Pseudo-Riemannian, Riemannian are different. Riemannian, Euclidean would really essentially be the same of this. And then what's left over? Well, k. So this is k. So this is the same thing as that really equals I cross j. So then what about the Hodge dual of j cross, of j, not cross, j k, right? So that would be epsilon j k I, like that. Then of course there's this 1, and then it's I. Well, jki, I guess I, jk, I have to go 1 flip, 2 flips to get I to the end. So that's even, so it's obviously I. So the Hodge dual of j wedge k equals I. So this is the cross product. Obviously, the Hodge dual of k wedge I is going to be j. So this is how you define mathematically, in a very sensible way, the cross product. What's important to understand, though, is that this idea of getting back to the vector, to the one-form space, or to the space of vectors, right? Not the one form, the one vector space. Going from vectors to forms back to vectors, or one forms to p forms back to one forms, that really only works in 3 dimensions, right? Because what if I had say, I don't know, 5 dimensions? Well, let's say 3 dimensions. Let's say 4 dimensions, right? I would do something. It would end up being, well, let's go back to dx0 wedge dx1. So that takes me from, well, okay, hold on. Let me do it this way. dx0 and dx1, those are 2 guys in, well, wait a minute, I want to use this, I want to do vector spaces, but I might as well, since I've started my example in vector spaces, let's do not the forms, but the vectors. So phi 0, partial 0, partial 1. I can take those, wedge them together, and I get partial 0, partial 1. So I've gone from 2 vectors in the first exterior power to 2 guys in the second exterior power. The problem is if I'm in four-dimensional space and I take the Hodge dual of this, I end up back something with z partial 2, partial 3, either plus or minus, depending on the metric. But that's still here, right? This is the Hodge dual operation. This is the wedge operation. So that's what this is, right? This is wedge, then Hodge dual. This is wedge, then Hodge dual. But I don't end up back in phi 1, right? Because the dual space of not phi 1, of lambda 1, the dual space of the second exterior power is still the second exterior power, because this is self-dual, right, in that sense. So I can't go from vector cross vector equals vector. I'm going from vector cross vector equals basically another vector cross vector, right? If I define the cross product as being the Hodge dual of the wedge, right, alpha, beta, if I define that, I end up with something in the dual space, something in the second exterior power of the vector space. So I can't really define a cross product, a clean cross product, where you end back up in the space where you began, except in 3 dimensions. In 3 dimensions, it happens to work out. Now, there's a way of it working out in 7 dimensions too, by the way, but it's not at all really analogous. I mean, this is just very clean and simple. The 7-dimension version is kind of nutty. It involves a clever observation, for example. I'm not saying it's not crazy. I mean, it really does work, and it's unambiguous. The point is you're forced from one dimension to one dimension. There's a logical way of getting back to not one dimension, the first exterior power wedge, the first exterior power. There's a logical way of getting back to the first exterior power, but it's a little more complex than this. But this is how cross products work. This actually is where cross products live and come from. It's this form of algebra that allows it to work. Okay, so with that, I'm going to close this lecture on examples of or demonstrations of the Hodge dual. In the next lecture, we're going to cover a different form of duality.